My name is Dirk. As I was introduced, I've been working at Flora Holland for almost 6 years now. I'm the team lead of a data science and data engineering team, some of which are actually here, if you rather want to have a chat about this later. And today I will tell you about, something we did in logistics. I think it's one of the cooler projects that I did with the team, of course, in my past 6 years. First, I will explain something about Flora Holland, what we do, and then go into what we actually did. So who of you knows Flora Holland already? Royal Flora Holland? Oh yeah, obviously. For the people who don't know, we're the largest international marketplace for plants and flowers. And we're also a big cooperative. We've been founded by the growers of the plants and flowers. And, well, that was over 100 years ago. What we do is that we offer a marketplace for people to offer their products and then sell it. But we also do a lot of logistics, supply chain. We're more and more becoming an international supply chain. And also, we also are sort of like a bank, because we also handle the payments between the growers and the buyers. So it's pretty diverse, I would say. But most people actually know us from this. This is a video taken almost 6 years ago. This is one of the auction halls. This was all before Corona hit the world. Nowadays, actually, the world changed a lot. People are working a lot more from home or in trade centers. The products are not going through the auction halls anymore. And we're becoming more and more a complete digital marketplace. So this is not exactly what we're doing anymore. But yeah, the idea of Flora Holland, where we are a marketplace of plants and flowers, still exists. So some facts and figures. I also stole this from our corporate presentation. We'll get to my own slides in a minute. Some numbers. We have about the auctioning itself is about 100,000 transactions every day on average. That happens in a time span of maybe 3-4 hours. And once that has been auctioned, all the growers that have supplied us, we will distribute it to the buyers. The plants and flowers come from, largely from the Netherlands, but also a lot international, a lot from Africa, South America. And then it all comes to the Netherlands, to one of our locations, and then, we sell it, and then it's being distributed across the world by the people who buy the plants and flowers. So now the question maybe is, if somebody from Africa wants to sell flowers to somebody in Turkey, why doesn't it go there straight? Why does it go through our building? And that's because we do a very granular distribution of all these products, right? We sell a large variety. In the previous sheet, I think there was 23,000 types of plants and flowers, and nobody buys a complete airplane of roses from Africa. So it first comes to Flora Holland as a logistical hub, and from there it gets distributed across the world again. So to explain maybe a bit how this works, the growers, they have supply, they grow the flowers and the plants, and then there's a bunch of buyers who wants to buy that. So what happens is, let's say this green plants company, they sell their plants through some direct sales channel. They have a direct link with some buyer and they want to sell it. So let's say this supply has been sold by a Europe trade lane. They can still then they can choose if they want to send the plants straight to the buyer, or they can choose to do the logistic through us. And the other company, Cool Flowers, they maybe want to auction their flowers. They didn't sell it yet, so they bring it to us, and we then auction it to one of the buyers. And while this is happening, we get supply that has been sold and has been unsold. We sell it, so maybe part of this supply is being sold to Europe Trade Lane, the other one to Nice Flowers, the other one to the Amsterdam Florist, which is just a local flower stall. Same goes for all the other plants. We can sell it very, very granular, like on the bucket or tray level, right? Now the question is, how do we distribute that? Because it's far too expensive to send it yourself. So we do this distribution for these growers, and we make sure that every buyer gets the flowers they have bought, right? So this is a very important part that we play in this whole supply chain. So we used to do it like this. In Dutch, we call it verdelen. which oddly translates to distribution, which is a bit of an annoying term if you do this talk in English, because well, we still do distribution, we just do it another way right now. We're transforming our company to more, I guess, traditional warehousing where we do order picking. And to explain that a bit, because we're going to talk a lot about order picking in a moment, what happens is that if a buyer has, or a grower has brought us some products, then some buyer will buy something, like say that there's a buyer X and they buy 2 orange buckets of flowers and they buy 1 purple bucket of flowers, then we can combine this into something called a pick list, and then some person in Florida will get this list and has to fetch this from our warehouse. So they take an empty trolley, they then get an assignment that says, okay, drive to this one location, take 2 buckets from that location, then go to the next location and take 1 bucket of flowers from that location, and then in the end they will deliver it at the end of our pick zone that they're in, and then some other department will take it and they will deliver it to the buyer. They all usually have a space in our building, and then it will be delivered there. So pretty simple, right? This idea. So it looks, our warehouse looks a bit like this. So there's a bunch of aisles, and there's on every position there's some trolley stored. In our system, we know what is stored where, and we have many of these places. Like our Aalsmeer site is about the size of Monaco in total in footprint, so you can think it's a pretty big location. A lot of this has to be stored in cool cells, not everything, but a lot of it stored in cooling area, which look exactly like this. Then some person is driving on one of these, what's it called, a trolley, or is taking a trolley on his cart, and they drive around and then do whatever I just explained. They also have a scanner, so that's the device that tells them where to go next, and that also ensures that once they scan their location, that they're at the right position. So we are now transforming into order picking, right? So some sites are already completely there, others are still in the process of getting there. So what is then the problem? Well, we think that the current process that we have, we can do a lot better. So most of us have actually been order picking, helping out in the busy periods, so we've experienced it ourselves. It's also good when you do a project like this to have experienced it yourself. But yeah, you would think that we're not the only one with a warehouse solution, right? So any web shop or well, Amazon, right? Or in Dutch bol.com or Coolblue or some supermarket, they all do this. So hasn't this been solved? Well, the answer is maybe it has been for those warehouses, but we're a little different than most warehouses. So first of all, we don't really keep a stock. Most of our products come in 24 hours before it's being sold, so we put it in our warehouse, and then it's being completely sold off again. And more importantly, our products haven't been sold yet at the time that we already start the process of order picking. So as the auction starts and all the transactions come in, these 100,000 transactions, that's also the same time that we already start doing this order picking. So in a traditional warehouse, usually you already know every transaction that's going to be done. You can optimize this completely and then run your process. For us, it's running concurrently, actually. And the other difference is also that in traditional warehousing, usually you have a buyer that buys as 1 transaction or maybe 2 or at least a low amount. Our buyers buy a lot of things over time. So yeah, it's a different optimization problem that we're trying to solve. Yeah, and there's been many improvements, ideas from the logistic department, but also from a data perspective, and they can be on any of these three topics. So we can change maybe the layout of our warehouse, the way that everything is stored in there. Maybe more aisles, less aisles, longer aisles. We can put different product groups together, so we can the way we put these trolleys with flowers in the warehouse. We can change that as well. But it's very costly to do this, right? Especially if we want to change the way the layout is, or we combine pick zones, or we separate them. That's an expensive operation. So if we want to try things with that, it's going to cost us a lot. It's really hard to iterate on this. Same goes for people. If you want to change the behavior of people, get them a different way of working, get them to do the task in a different way, that's also a very costly operation to change the whole workforce to this new thing. And even when you do change, probably in the first few hours or first few days or weeks, it's not going to be exactly in the way you intend because they have to adjust to this new way of working. And then we come to IT, which you would expect maybe would be the easiest one to change. But yeah, we're dealing with a supplier that delivers a warehouse management system to us, and it's very hard to make changes in that to make it do exactly what we want. Also because we're such a special case of warehousing, I suppose. So yeah, in all three areas, if you want to make a change, it's very costly to do so, it's very costly to test, and we have no data to back up our decision to go for one of these things. So yeah, that's what Project Picard is about, to instead of having this gut feeling changes, to make more data-driven decisions. So we want to already test our ideas before we started implementing them. Well, that's where we started building this order picking simulator, or Project Picard. People who have seen me talk before know we give every project a special name. This one's called Picard. The idea is that we built a simulator that could simulate this warehouse, so our buildings, the people that work in it, and also the IT systems. It also means that we can have an environment where we can control everything that's happening. So for us, one day to another day, the operation can be completely different in the way that the supply changes, or we have more experienced people working that day, or there's more transactions. So it can all vary day to day, but here we can keep everything the same. And it would also be very easy for us to make changes in this and start, test and validate new ideas, right? So we set out on this path. So first up would be the warehouse itself. So we have a lot of technical drawings of the design of how our warehouses are implemented, so we started off with that. And then we needed some way of describing this in our simulator, to describe some new, or describe all of these storage positions. And we thought of some ways of doing it. You could just code it, right? You can just make some code that describes this warehouse. I think a better idea would already be to make some UI where people could just, click the warehouse together almost. But yeah, that's a lot of work to implement as well, and we're not front-enders. So we went to the one tool that does it all, that everybody knows, that also people from the logistics department know and understand and can work with. That's Microsoft Excel. It's maybe a bit silly, I realize that. But the picture that you see here is one of our test cases in the simulator. It's pretty small, so I could really put it big on the screen. So this describes for us what a warehouse looks like. We could input there what the storage positions are, what the aisles are, and what the driving directions are, because there's like specified, you can only drive in certain directions in the aisles. So we can completely describe a warehouse in this, and I realize that Excel is not meant to be used for data science or anything like that. But our logistics department can work with this and can provide us they can make all the warehouses for us. And then our code just reads this thing and parses it into an actual running warehouse. So that was actually a pretty useful, quick way to build this. Then there's the people. We need to simulate them as well. So the first thing we had to do was estimate every step in the process that somebody does to order pick some products, right? They get a new assignment. They usually have to then fetch a new empty trolley. So if they drive there, take the trolley, hook it up to their cart, then drive to some position. They have to get there, scan something, then take the trolleys, confirm that they did it, and then they get the next assignment, right? They go through their list, and then they go to the printer, and then they have to deliver. They have to do a check, and then they deliver it. So every step, we need to model this. So luckily, these persons are having scanners in their hand, so we know every time they went somewhere, we know the time at which they were there. So we modeled their whole workflow, and then we ran a big regression on that, and then we came up with this model that tells us how long each step takes for them to execute this. Yeah, the problem is we only have one scan per time they pick something, so that's a bit bad, and there's a lot of noise in the data, as you can see. So we actually improved that by putting a location beacon system in one of our pick zones. And there we could get every order picker, we could give them a tracker, and we could basically follow them throughout the cool cells. And it helps us to narrow down this noise or filter out some weird things that are happening. Using this positioning system, we could just clean up our data, more or less. And once we have done it, we have to think about, okay, we have this warehouse, and now we have to have people drive in it. So that's when we started thinking about driving algorithms, which was a pretty interesting exercise as well. So we didn't want the order pickers to just run through the cool cell and drive through each other. We wanted the interaction to be there as well. Because if you want to speed up your process, you can put more people in it, but at some point they will just clutter up, there will be a lot of congestion, and they will start waiting on each other. So we wanted to have this interaction in the simulator as well. We started modeling that. So as you can see here, every dot is like an order picker, and they now start driving around each other and interacting and waiting for each other, which also was quite the adventure to implement this, because sometimes, they start to want to go in each other's direction now, and then, you enter in this gridlock. I think I speed it up in a moment, and then your simulation just, it stops because everybody is just stuck in traffic. So yeah, it was quite the adventure to program them to do what you want, and they never do what you want. So it feels like they're actual persons when you start working on this. Once we have this, we have a warehouse, we have people able to drive around in it and not crash into each other. And then we go into the IT. So what we wanted to do is to recreate the algorithms that we have in our current warehouse management system that's currently being used to make these pick lists and everything. It's called a waving algorithm. I'll explain it. The reason we wanted that, of course, is that we want to have a baseline to compare our new solutions against. So what happens if somebody buys something? Let's say somebody buys 3 buckets of these orange flowers. We need to decide first which trolley are we going to take it from. That's called allocation. So let's say we allocate it to this. We allocate it to this trolley. Then maybe somebody buys some other flowers and somebody buys some plants. And we can all allocate it through all the trolleys in our warehouse, right? Then we have to think about how are we going to combine these transactions onto trolleys for this buyer. So if you think about it, you can do it in various ways. I mean, I put down 3, but you can think of even more, of course. We can have different configurations. So all these trolleys are at a certain location. They have different deadlines of when it has to be delivered, usually within 3 hours after it's been sold. There's a lot of values and parameters that we need to take into account to decide what are we going to combine. So this is called the waving algorithm that does this. And we implemented the one that we have in our current, we basically mimic it. Once we have all these 3 things, well, then we're done. We built this completely in Python by ourselves. We used SymPy as the framework. Don't know if you're familiar with it. If you have questions about it, I have some bonus slides about it. And we can change anything about the simulation, the number of people, how fast they work, how we put trolleys into the warehouse, what waving algorithm we use. We can change anything on the simulator and run any configuration and compare it to, reality, right? And then we get also all the data we want from this, and that's new because that's something we don't have for a new situation. If we want to make a new pick zone or anything, we don't have any data, but through the simulation we can now, we can see what happens if we make that change. All this data, we of course don't want to analyze by hand every time we run something, so we also made some dashboard in Dash that can take all this data and you can compare everything on the main things you want to know quite easy, and you're always capable of going into the data yourself again. And then the last thing that we also did in this dashboard was some debug window. Because sometimes these order pickers do things you not expect, or the results are somewhat unexpected, and we want to be able to check what went down, what happened. So yeah, we made this debug overview. So for any simulation that we run, we can, for any pick zone, look at it over time, what happened. We can see what the order pickers are up to, what they want to do. And we can just, in general, compare what happened. And well, if there's some congestion or people are waiting for each other, we can check what caused all of this, and maybe change our algorithm or do something about it. So yeah, that's a simulator. So at some point we were able to simulate reality. We looked at data sets. We loaded in data sets from some actual days, and then we check if we run this simulation, does it match what happened in reality, right? In terms of all kinds of metrics that we use to measure our performance of our logistics process. So, but then we got it pretty close. So then the question is, if we have this system and we want to make changes to it, so what is within the boundaries of our building, what is the most optimal thing that we can find? Like, if we are free to drop all of these restrictions that we have in terms of changing buildings, in terms of training people, if we want the IT, which we can't change a lot, what if we drop all of these restrictions and we're going to model this process in a way that we want? Well, we took a week to find out. It turned out to be more difficult than a week would take, so we worked a bit longer on it. But at least the basis for all of this was laid in the first week, and then it was all debugging and figuring out what actually was going on. So yeah, we took some time to do this, and then your first question is, what are you optimizing for? What is the goal of this thing? So these are the metrics that we focused on. So the primary objective for us, it's also about costs. So we want to minimize the number of hours spent by the workforce. So if less people, or if we need less people, or they are faster or more efficient, it costs us less money. So we want the least amount of total hours worked by the total workforce. But there is a hard constraint on this. We don't want to deliver things too late. Like I said, usually we have 2.5, 3 hours to deliver something to the customer, so we need to be on time. And then our KPI that we are monitoring in reality is that we 98% will be on time. So that's a hard constraint. We can't just put one person in there and let them do all the work, or her. We do have to be on time. And then the secondary objective is the expansion factor, and that requires maybe some explanation. If you remember this slide, I presented it earlier, so you should all know it. We started out with 3 trolleys, right? The growers delivered us 3 trolleys, but once we have distributed it, it now became 4 trolleys. So that's an expansion of the number of trolleys used. And we want to keep that number low as well, for various reasons. One, we have to transport less air, and that takes less time to do so. And our customers are also happy because they also have to do less handling when they receive all of this. So we also keep an eye on this number, because it's important in the processes after we're done with the order picking. Yes, so again, we had to think about, okay, what are we going to change about any of these 3 things to make it more optimal? And we focused a bit on the warehouse and the IT parts, and not necessarily on the people, but more on the warehouse and the waving algorithm. So the warehouse was first. So these are the top 3 are 3 drawings that are actual pick zones in our site in Naaldwijk. And they are separate pick zones. So if a buyer buys something that's stored in all 3 of these pick zones, then we need at least 3 trolleys and 3 different pick lists to run this. And we can see from the data that some bigger pick zones are more efficient in the way they are run. So what we thought was, okay, maybe we can combine these 3 pick zones in one giant pick zone, and it will be more efficient. So that was our first idea of optimization. So if you remember the Excel sheet, that became pretty interesting Excel sheet to create. But it worked, so that's good. Yeah, and then the waving algorithm, and that was, we had bigger ideas about this, and I will also do a bit of explanation about what we changed in the algorithm for this. So, the problem we're trying to solve is called the vehicle routing problem. I don't know if you know it. Most people probably will know traveling salesman problem. This is basically the traveling salesman problem, but then the salesmen have a capacity issue, so they can't just take everything. And you probably have multiple salesmen to run this. So what you see here is one of the pick zones. It's an example from actual data. And every purple dot in this means that you have to do a pick for one specific buyer there. So it's all for the same buyer, and you have to visit every of these locations because they bought at something at every of these locations. The number in the orbs, in the circles, that is something that tells you about capacity. So 100 would mean that it would fill a complete trolley, and you can only fit that onto one trolley, right? So that's what's being shown here. And then the question becomes, what's the most efficient way of picking this? And I think if you count up all these numbers, you would end up at 440% of a trolley. So that would mean that you would need at least 5 trolleys to be able to pick this, because it fits you have to use 4.5 trolley to fit this on this. So yeah, the question becomes, how can I do this so as efficient possible? Pretty interesting. And then efficient, you can think about, I want to use as less trolleys as I want, or I want to drive the lowest amount of distance as I want, or I want it to be the fastest. Well, you can think of every single parameter that you want to optimize for. We chose least distance driven. So yeah, when you run a solver for this on this, it distributed like this. You get 5 trolleys. I don't know if the coloring, you can see it well, but everything that has the same color will end up on the same pick list and thus on the same trolley. I don't know if anyone sees maybe something interesting about this, because usually people notice. It's this, you have here this blue one that's 63, and you have a blue one that's 35, and then here there's another one that's 63. And that was quite interesting to us. Like, these are very close together. Why isn't it, why aren't they put on a list, and why is it put on the 63 list? So we started investigating a bit, and you always find that an algorithm is smarter than you are. So if you take the routes to pick this up, then this would be the route you would take. You would go from the empty trolley pool, go to, for the blue one, first go to the 63 one, then come back for the 35, and then deliver it, or go to the printer. And then for the yellow one, you would just pick that one up. Now, if you compare this, against if we would swap it, which would look like this, then you could see that you're driving a lot more vertical distance in this example. And also you have to drive a bit further from the 63 to get this 35. And it's because of these driving directions that we have that you get this super counterintuitive things. But if you check it, it actually makes a lot of sense. So yeah, we organized an algorithm that runs like this. Put it in there as well. We put in the bigger pick zone. And then we had one more thing that we wanted to tackle, which was the congestion problem. So what we see a lot, this is a picture I took once, probably at very early in the morning. What you see sometimes is that all the order pickers are being, usually at the beginning or at the end, but also less extreme like this, but also during the process you would see this as well, that order pickers are being sent in the same aisle or to the same storage positions, and then they have to wait for each other, and that's, well, idle time is useless. So we want to prevent this, right? So that's something we wanted to tackle as well. And what we came up with was that in the simulation we know, of course, everything that's going on, right? But we don't want to use this because the solution wouldn't transfer to reality where we don't know where everybody is all the time. So what we decided to do is take this cost model that we built, and then we would use it. Once an order picker gets a new pick list, we would estimate where this order picker will be at any point in time, and then ensure that not the same people will be sent to the same areas at that time. So that's something we built as well, sort of a traffic controller that makes sure that people distribute better over the pick zone and not go in the same, all be in the same area at the same time. So these were 3 base ideas for this optimization. So we built all that, and then we started to run the simulations to see what would happen. I will show you the results for one day, but of course we want to run this over a longer period of time. So yeah, 4 different configurations. So we have the original waving algorithm that we're currently using, and we have our improved algorithm with the vehicle routing problem solver and the congestion control. And then we ran them both with the separate pick zones and with the giant XXL pick zone. So those are our 4 comparisons. And the top one would be the baseline, right? That's what we're currently doing. Well, what we immediately noticed is that our current algorithm doesn't deal very well with these giant pick zones. It uses some sort of a greedy approach to make these pick lists, and it also doesn't break open the pick list anymore once it has more information. So we already thought that it wouldn't probably work very well with a very big pick zone, and it turned out that this was also the case. So yeah, that one we'll just scratch off for the rest of the talk. And just as a reminder, these were the metrics that we were optimizing for. So least amount of hours spent and not a lot of trolleys, or not a big expansion factor. So if we look at the results, yeah, this maybe a bit of a boring figure, but if you look at the results that we got out of this, we saw that, well, we look at first at total hours spent. So we see that from our original solution, the current simulation would actually run about 15% less. We use 15% less hours in this new solution. And for the giant pick zone, if we use our new algorithm.
What's the weighing in the primary and secondary constraint?
There's no weighing. We run it and we look at the, we optimize for distance. And then we run the simulation, and these are just outcomes. So we don't steer the algorithm anymore.
You have to give like a cost function, right? You have to give the cost to the primary.
Okay, yeah, so the question, maybe I'll repeat it. Yeah, the question is, what did we use to then as a cost function? Well, the cost function would be that we, in the vehicle routing problem, we minimize distance driven. So that's the model that we're currently using. We thought about expanding this to have other things included as well, like how many trolleys and all, less air. But that's the one that we try to minimize.
And if you have 2 trolleys, the distance driven is like duplicate, or?
Well, you have an overhead. The more trolleys you have, the more overhead there is. So we try to well, if we thought there's a lot of time goes, like the 2 biggest time sinks are driving and waiting basically for other people, well, and transferring buckets, but you have to do that anyway, so that it's not really we cannot really optimize that. So distance driven if we bring that down, we would bring the time down as well. So that was our idea. So if we run it, then well, these are the results. So for just doing the algorithm and the congestion, we would get 15% a more optimal process, and for the XXL pick zone, we thought that it would be the best one, but it wasn't if you look at total hours spent. So that was quite interesting. What we did see is that everything is on time. Like we lowered the amount of order pickers until it wouldn't be on time anymore within the 98%, and that would be the minimum. But if we look at this other secondary objective, we see something interesting, because in the fastest one, the 15% better one, we noticed that the expansion factor didn't really drop. We only have a small drop in the number of trolleys that we actually push out of our pick zones and have to be delivered. But for the other one, the XXL, and you would expect there that the expansion factor would be lower, we see that there's a reduction of 22% in trolleys that we put out there. Now the question becomes, of course, what is more interesting? Like, is it this total hours spent by the workforce, or is it the number of trolleys that the output? Because we need less space, we need less of these trolleys, because the trolleys are all ours. And the department who's running the process after this also has to do less work, and probably the buyers are also more happy. So we think that, well, that's I think something for logistics to decide, and maybe further investigation, that, well, this 15% is probably going to weigh more than the 22 here. But yeah, that's something that we have to discuss with the logistics department, I guess, what they think is best. Yeah, and then where does this improvement come from? So one part of it is, as I said, the driving time. So we see that in the 15% improvement, we indeed drive a lot less. And in the big XXL pick zone, we drive a lot more, which is to be expected. But we thought that because of the efficiency gains we get from having a big pick zone, that we would gain that back. But clearly, this was not completely the case. So driving time was one metric that we improved. And the other one that I talked about was congestion. And there we also have an example. So here we see, it's a bit, it's not really cherry-picked, but I picked this part of the process because we saw this across the board. On the left side, you see a pick zone that's the original algorithm, and on the right side, you see our new algorithm with the congestion prevention. And what you could see is that the order pickers are way more distributed throughout the process. So there's only a small part of it, but throughout the process, you see that they're better distributed across the whole area. And that means they interfere less with each other. Well, on the other one, we see that they are a lot in the same zones for all kinds of reasons. But that's definitely something that we're happy with. That was what we're aiming for. So that helps a lot as well. We gain a lot of time there. So almost done. Then, what are we up to now? I think we want to further dive into this data and validate it more and get it more, get it to as close to reality as possible. We don't want to be exactly on the ball with what the reality happens, because there's a lot of noise happening there, people working at different paces. But we at least want the improvements that we do, that they are transferable to reality. So that's what we're working towards. We got a lot of requests for use cases, smaller use cases that we want to do. And I think a lot of other cool features that we could do would be that the order pickers do more dynamic routing based on how busy it is. Like if you're order picking, you see a busy aisle and you have to go through it, you probably drive around it because it's so busy. So we want to get those type of features in as well. And in the end, get it all run in the cloud so people who are not developers can also run their own simulations with their own configurations. So we're running all on Amazon, so maybe we should have a chat on how to best do this. But that's I guess what we're up to. And that will be the end of my talk. I hope you thought it was interesting.